Picture of health, image display software that could save time and lives. An eye to science, modeling the building blocks of vision and learning. Probing the bounty, a corn kernel's interior revealed. SuperQuest 91, training tomorrow's scientists and engineers.
Boston, Massachusetts, home of Massachusetts General Hospital, one of the oldest, busiest, and most advanced medical facilities in the United States. And inside the hospital, radiologists are quietly carrying out an experiment which, if successful, could transform the tools and techniques of their practice.
Anything which can lessen the burden of tracking films is potentially a tremendous help to us. A film which arrives 2 hours after a patient is seen in the emergency department might as well not arrive at all.
To hasten the retrieval of radiological film needed for diagnosis, Mass General is developing a computer network called the Radiology Storage, Transfer Analysis and Recording Project, or RSTAR.
We just have too many images to manage. Our film library is over in Somerville, and it's a half an acre. We have about 50 film librarians that run around all day long putting the images up in view boxes for radiologists to view. What putting it on a computer system would do is it would allow this image to be wherever it needs to be.
Aside from speeding up the tracking of X-ray films, the RSTAR network could improve the diagnostic capabilities of smaller hospitals and clinics by connecting them to expertise at Mass General. Dr. Daniel Rosenthal, an orthopedic radiologist, typically screens about 150 X-rays every day. His department generates over 300,000 X-rays every year. Storing the X-rays in a digital library will save vital time and space. But first, analog X-ray films must be scanned and digitized before they can be sent on the network. Once entered on the RSTAR system, the digitized images can be manipulated and transmitted.
The ideal system would allow a presentation of a current image and a comparison previous image in the same format, preferably with the same size, and it would be instantaneous, and preferably it would be linked with the rest of the information management system of our department. Things such as, for example, prior diagnoses on such a patient, historical information, pathological findings, and so on.
But the RSTAR group had difficulty locating a software tool that would provide quick access to both images and patient data in a single file format or folder.
What we wanted to construct was a system that was very open-ended, where doctors could place anything they wanted into a folder so that another doctor could look at it later.
Sean Doyle learned of an NCSA software tool called Hierarchical Data Format, or HDF. HDF looked ideal. It's designed to store a variety of data types, everything from scientific visualizations to multidimensional data sets.
HDF is available in the public domain, and anyone who wants to use it is free to use it. That's part of the philosophy of the way that we work in this group. Anyway, Sean found HDF, read the documentation, and saw that this was really the kind of thing that they needed. The only difficulty was their data was a little bit different from the kind of data that we're used to handling, but since HDF is extensible, they're able to extend it to handle the kinds of data that they're using.
HDF is also portable to any computer platform, an important consideration for the hospital.
What HDF provided was a way of having a uniform access to data on both our VAX machines and on Macintoshes, and we're very concerned about having software that runs on lots of different machines and being able to send data between different machines. For some image processing things, we have it done on our VAX. When we're displaying it, the information's on a Macintosh. In the future, there'll be other machines on the network.
While the RSTAR group is still refining its image processing techniques and enlarging the network, the system is already in action.
We are actually on the very verge of having routine access to our warehouses for the emergency radiology department, so that digitizers have been installed in the major warehouse, which is located in a suburb called Somerville, and output devices are present in our emergency radiology department, so that it will cut the time when a request is initiated until an old film is received from hours to minutes.
Mass General is currently conducting a field trial with an HMO clinic in an outlying region of Boston. The clinic transmits digitized X-rays and patient information over the network to Mass General for diagnosis.
The preliminary interpretation is dictated by telephone directly into their digital transcription system. Compared to previous films obtained 2 days earlier, there has been a new cast applied to the left leg. Period again noted. It is then immediately available to the clinicians at the health center by telephone access. Subsequently, a second radiologist is dispatched to the site, who then looks at the analog images and generates a second independent interpretation, and the two are compared. The discrepancies have been relatively few in number, and the vast majority of them, in excess of 90% of any discrepancies, I would say, are due to differing interpretation of the finding, not due to any difference in the appearance of the image due to the transmission.
To Dr. Rosenthal and his colleagues, the prototype radiological network holds great promise for the future of HMO medicine.
What one would like, basically, is to be able to deliver tertiary care expertise in a dispersed manner to all of these health centers. And so, for this reason, I think that the digital image technology is likely to have a tremendous impact on the entire HMO world.
Klaus Schulten, his daughter Charlotte, and their dog Floppy take in the sights of a warm summer evening, unaware that a fuselage of electrical impulses triggered by light underlies their sense of vision. Exactly how the brain processes what we see is an age-old mystery, one that Klaus Schulten, theoretical biophysicist, is attempting to solve.
I personally believe that biological intelligence, which manifests itself in vision, is realized on many layers of organization. It starts on the molecular layer, actually at a point when light interacts with the organism in the retina of the eyes, and it ends up with a multicellular layer where many cells are involved and cooperate in processing on the visual information and leading to suitable responses.
Schulten heads the Theoretical Biophysics Group at the University of Illinois' Beckman Institute for Advanced Science and Technology. The group uses the tools of high-performance computing to study the primary physical events behind vision. Group member Andreas Windemuth is studying the molecular dynamics of bacteriorhodopsin, a bacterial protein that is closely related to the light receptor proteins found in all species capable of vision.
What people are currently focusing around is the central process where the retinal molecule, which is a little part inside the protein, absorbs a molecule of light and changes its form in response to that. And by an almost mechanical mechanism, transports a proton from one side of the rhodopsin molecule to the other side.
Simulating the proton pumping mechanism of bacteriorhodopsin required evaluating approximately 2 million interactions between the 2,000 atoms of the protein in one time step.
You cannot simplify the system. That's what it is, and you have to describe it in its entirety. It was impossible by experimental means, at least to this point in time, to see the complete structure of the protein. So we also had a complete structure with a computer. The computational tasks involved are actually rather large, and it requires, therefore, the very best computers we have, particularly the massively parallel computers like the connection machine.
Moving beyond the molecular level, Klaus Obermeier is exploring how the brain processes the electrical impulses once they are triggered in the retina. According to observational data, the signals from light receptor cells give rise to ordered patterns of electrical energy in the visual cortex, which in turn correspond to the arrangement of retinal cells. Most of the neural connections required develop and mature only after an animal is born.
If an animal opens the eyes and sees something, then the visual input comes to the brain, then important aspects of this visual input gets imprinted in the brain circuits and form the structure, which then actually can process visual information.
Obermeier implemented a neural network algorithm that takes advantage of the connection machine's massively parallel architecture. The algorithm maps 2 cortical neurons to a single processor with possible connections to 900 simulated retinal cells. To test whether the neural network algorithm properly models the visual development of a young animal, Scholten and his co-workers simulated a robot that uses the same algorithm.
The robot actually also has to learn to see through the 2 stereo cameras. It literally has to connect the backplanes of the 2 cameras with the brain, a kind of data structure, which is in the computer connecting the cameras and the robot. But it also applies very similar rules to generating then signals which run to the motors of the robot to make the joints move.
After 600 learning steps based on visually monitoring its errors and computing better responses, the robot can easily grasp the cylinder seen by the cameras. This demonstrates that the concepts contained in the neural network algorithm are indeed viable and can serve as a learning scheme for the robot. But would the neural network program work on industrial robots? Scholten assigned Jörg Walter to experiment with a motorized robot arm equipped with a computer brain and 2 stereo camera eyes. Again, using the connection scheme of the neural network, the robot calculates its errors repeatedly and learns how to orient itself to an object. Recently, the group purchased a pneumatic robot arm to experiment with more complicated tasks. However, while such robotics research could benefit industry, the driving impetus for Scholten and his colleagues remains the quest to understand, from the molecular level to the multicellular, the myriad interactions of that ultimate computer, the brain.
At the very heart of science are discoveries, basically to discover continents of knowledge. And you always need tools like sailing boats to reach those continents. I like to view the computer as my sailing boat with which I can discover new intellectual continents.
Autumn in the Corn Belt, and the farmers are racing the changing season to reap the fruits of their labor. During most years, the drying capacities of local grain elevators are stretched to the limit as they ready tons of still moist field corn for market.
We do something on the order of 50 to 60% of our business volume in inbound receipts in about a 45 to 60-day period of time. We'll need to condition grain with moistures in excess of about 15%. You cannot sell corn overseas into the barge market, into the train market in excess of 15%. Obviously, the reason for that is that it's fungible. It will deteriorate while en route to its final destination.
As a result of the rapid drying process, the corn kernels frequently develop stress cracks or fissures. When corn is exported, it undergoes extremely rough handling from port to port. This results in the stress-cracked corn breaking apart during overseas shipment, lowering the overall quality of the export crop.
There have been concerns for many, many years that the quality of our corn was not equal to that from other countries, and as a result we were losing market share. Clearly our corn arrives in worse condition than that from South Africa and Argentina, where the climate is such that they may harvest corn at 12% moisture from the field, and ours frequently comes in at 25 to 30% moisture and must be dried.
But how can the moist Midwest corn be dried quickly without causing stress cracks? Improving current drying practices first requires a thorough understanding of the physical causes of the cracking.
We're approaching it from many different ways, but one of the things that we're doing is this fundamental study using magnetic resonance imaging to see how the moisture leaves the kernel and where and when the cracks appear during the drying process.
By applying magnetic resonance imaging, or MRI, a technology originally developed for biomedical imaging, Professor Bruce Litchfield can probe the moisture gradients inside a corn kernel as it's being dried.
We haven't had a technique that really allows us to measure those moisture gradients during the process without destroying the kernel in some way. And with something as small and complicated as a corn kernel, once you cut it open or do some other destructive test, it changes everything. So being able to measure it non-destructively is very important.
Litchfield and graduate researchers conducted a series of experiments at the Biomedical Magnetic Resonance Laboratory at the University of Illinois. Here, they developed a drying system that attaches to a microscopic MRI probe. Once placed inside the probe, the kernel is dried down from harvest moistures to a moisture content acceptable for storage.
Then we could measure the moisture gradients or the change in moisture during the tests and see how the moisture gradients were related to the moisture transfer.
These are a series of slices from a three-dimensional data set. And in this case, the slices are made through the kernel, beginning at the top.
As a result of the ongoing collaboration between the Biomedical Magnetic Resonance Lab and the NCSA, Litchfield was able to easily create these scientific visualizations.
Within 3 years or so, we've built up a software environment for doing image reconstruction, doing data analysis of these imaging data sets that are produced by the laboratory. It's allowed a lot of investigators like Bruce Litchfield to go in there fairly quickly and efficiently without having to write any software and to do image reconstruction and to do visualization without a lot of effort.
We were able to reconstruct the images. It's a fairly computationally intensive process and make a series of images showing how the moisture was leaving and how the cracks were appearing. We use a technique of subtracting images from the original image of the kernel, and by doing that we can see paths of moisture flow and imaging of how things are changing during the process.
We found that the moisture leaves the kernel by going out through the pericarp or traveling in along this tissue and out the tip cap. When it does that, when the moisture leaves through those two mechanisms, it leaves some wet and some dry regions, and the difference between those wet and dry regions are where the largest moisture gradients are, and that's where the cracks appear.
We're working on control systems to control dryers and looking at different or new processes to dry corn, and so it's helping direct that. It also helps operators of existing dryers know that they can control their dryers in a certain way and thereby reduce the moisture gradients in a kernel, especially for that corn that needs to be exported or handled multiple times before it's used.
The work that Bruce Litchfield is doing is one piece of the puzzle that tells us what can we change in the handling and drying of corn to make it withstand the normal handling practices and deliver it to our foreign buyers in as good a condition as our competition.
You know, this is great experience because I've learned so much just about computer systems in general since I've been here. I'm not a programmer, you know. I just kind of look at the thing and say, yeah, that's kind of neat, you know. But I've learned so much since I've been here, and it's definitely a confidence builder.
I've seen visual models on the computer, and I really never thought about that. And I mean, it's just opening my mind to different things you can do with a computer, and I probably would never have thought of.
Space exploration, solar cells, robots, traffic jams, wetlands, and chaos. All are fair game to 11 distinctive teams of high school students and teachers. From all around the country they came, the winners of SuperQuest 1991, a National Science Foundation-supported high school science competition. For 3 intense summer weeks, the teams strive to master, then apply the tools of computational science to their own research projects. At their disposal, the state-of-the-art computational facilities at Cornell Theory Center, the Alabama Supercomputer Network and the University of Alabama in Huntsville, or the National Center for Supercomputing Applications at the University of Illinois, Urbana-Champaign.
It's exciting to know that you're actually learning this stuff, and that when you leave the 3 weeks, to go back home, that you will be able to say, hey, I can do that. I can run the supercomputer.
And we want to inspire these kids that anything is possible on their machines. They can just do what they want, and that even at that age, they can take this on. And when they go to college, they're already kind of ahead of the game there.
The new way of doing science, using computers to get your solutions, has just taken hold among scientists themselves, but there's going to be a need in the future for more and more scientists to do this. And we feel the earlier we can get students involved in using computers and their high-end, the supercomputers, the better off it'll be for the scientists themselves and for the country.
Amid mounting concern that too many high school students give up on science, programs such as SuperQuest aim to help reverse the decline and raise the level of achievement.
Many students have potential to go on to scientific careers, yet that potential isn't realized because they never get excited about it. There's no way something from over here is going to come out. These things go in straight line in space. This type of project and science fairs and other types of summer programs where students can go to universities and witness research firsthand and even take part in it a little. That's exactly what we need to foster a future generation of scientists and engineers in our country.
Aside from gaining access to advanced computing resources and programming support, students were also assigned mentors, each a specialist in the chosen project field.
What I thought everyone would be, computer whizzes, and they would just sit in front of the computer and pound away at math problems and all that stuff, but no, it's not like that. We met a lot of new, interesting people. It's really, I think that's the best part about it.
Yeah. It doesn't have a grip at the moment, but
immersed in a high-powered interdisciplinary research environment, the students began to appreciate what it takes to be a working scientist, experience that will serve them well in their future careers.
I think they've learned a lot about the integration of sciences. That physics is more than just gravity and things, that they can integrate their biology into it, their chemistry into it. They can find things that they're interested in. They don't have to stick right in the physics box.
I think they have a better concept of what it means to be responsible. I mean, they are responsible kids, but they were responsible basically for themselves. Yeah, they were responsible for themselves here, but yet they were responsible for the school, their team. Here we had these kids from all over the country come together, and they're a team now.
Here you are expected to work with each other, you're expected to learn from each other, you're expected to ask questions. We treat them as professionals, and that's a very important maturing experience.
In addition to getting their applications up and running, the students faced yet another challenge: to present their results clearly and concisely to mentors, peers, and teachers. Essential to a successful career in research, effective presentations demand preparation and practice.
This is real life. This is what people do. This is how people make their living, and you're seeing that, and you're getting a chance to involve yourself with it. I think that's the greatest thing I've gotten out of this.
It seems odd that we would not use gravity to further our explorations in space.
Soon enough, it was time for the final presentations. On the Summer Institute's last day, students at each of the 3 centers shared their project goals and preliminary results.
The telescope that I'm doing is of a new design that hasn't been...
In fact, much of the research will be done at the student schools. During the academic year, workstations are to be installed at the schools and linked to the supercomputer centers via national networks. Such connectivity will enable the students to continue to access machines, mentors, and other experts, regardless of their school's location.
When they come back, they'll tell their friends that, hey, it was pretty neat. And that's important. The school will benefit because other kids will hear it from their peers, that it's okay to be involved in science and to like it.
However, it's not just the students, but the teachers, their colleagues, and the schools that benefit from the SuperQuest experience.
At the end of the year, the workstations remain in the schools. A lot of those students may have gone on to college, and we are left with a teacher at that high school who has some very good workstations and a lot of knowledge about the use of supercomputers, and we stay in touch with them for years to come.
Look at what they've experienced. It's great. And then on a personal thing, I mean, I had a ball playing on the computers. I mean, I've been away from it for 3.5 years on a day-to-day basis, and I've got that bug again.
I would just like to see more people involved in supercomputers, and of course, we know that's not only the tool of the future, but the tool of the present. I think probably every occupation will in some way involve computers, and people just need more involvement, need more experience with using them.
In fact, it's hoped that the SuperQuest program can be further broadened to include a greater diversity of teams from a lot more states.
I think that many schools stay out of SuperQuest because they think that projects to win SuperQuest have to be very esoteric. And I think the point that we want to make is just the opposite, that the project that grows out from the student or the teacher's interest usually is the best project.
You don't have to know the computers. I mean, don't let the word computer or SuperQuest, you know, supercomputing, scare you. Don't, because there's so many people here to help you. They'll teach you. Try it. Get your kids involved. Who knows? You may be here. I mean, when I first looked at it, I said, no, there's no way we're going to win. And then when we did, I mean, I told you, it's great. Try it.
If you would like to know more about the activities featured in this program, please contact NCSA at the following address: